All right, let's dive right into one of the coolest puzzles in physics. It's a real head-scratcher where squeezing something actually makes it push less, not more. We're talking about the Venturi Paradox, and we're going to break it all down.
So here it is, the big question that messes with so many people's intuition. You know when you put your thumb over a garden hose and the water shoots out way faster? That makes total sense. But, and here's the weird part, what if I told you that the pressure in that super fast stream actually goes down? It just feels wrong, but it's 100% true. Let's get to the bottom of why.
Okay, so let's set the scene. Just picture a fluid, let's say water, flowing along nice and smooth. It starts in a wide pipe, and then it gets funneled into a much narrower section. The simple observation is this. As the water speeds up in that skinny part, the pressure it puts on the walls of the pipe goes down. And that right there is the paradox.
And this slide just lays it out so clearly, doesn't it? In the wide part of the pipe, you've got slow-moving fluid and a pressure gauge that reads high. But once it hits that narrow section, the fluid speeds way up, and boom, the pressure just plummets. This isn't just a theory, folks. You can go measure this. It's a fact. So what in the world is happening?
Now, if you've taken a physics class, your hand might be shooting up right now, ready to yell, Bernoulli's equation. And you're not wrong, kind of. Bernoulli's principle is the go-to formula that perfectly describes this whole speed and pressure relationship. But here's the thing. An equation tells you what happens. It doesn't really tell you why.
And this quote just hits the nail on the head. It perfectly captures that frustration. Just saying it's Bernoulli's principle is sort of like answering, why is the sky blue with because it's not green? It's a description, not an explanation. It doesn't give us that deep, satisfying mechanical reason. We want the cause, not just the name of the rule.
So here's the real deal with Bernoulli's equation. At its heart, it's all about the conservation of energy within a fluid. And it's totally correct and super useful. But it's describing the outcome of something more fundamental. To really, truly get the why, we have to rewind a bit, all the way back to the most basic laws of motion.
So, where do we find the real answer? Not in some complex fluid dynamics textbook, but with good old Sir Isaac Newton. This is where we uncover the actual mechanical reason for that crazy pressure drop.
You remember this one from school, right? F equals ma. Force equals mass times acceleration. Basically, nothing changes its speed or direction unless you push or pull on it with an unbalanced force. To make something accelerate, you have to have a net force. That is the absolute key to this whole puzzle.
Okay, now let's use that law. Imagine a little chunk of water, a parcel of fluid, as it moves from the wide pipe into that narrow part. We already know its speed increases, right? Well, any change in speed is, by definition, acceleration. So it's a fact. That little parcel of water is accelerating.
And if it's accelerating, Newton tells us there has to be a net force making it happen, something pushing it forward more than it's being held back. In a pipe full of water, where can that force possibly come from? Well, it can only come from one thing, a difference in pressure.
And here's the logical chain broken down step by step. It's beautiful. For our little parcel of water to speed up, the push from the pressure behind it must be greater than the pushback from the pressure in front of it. That's the only way to get a net forward force. So, it logically follows that the pressure up ahead in that narrow section has to be lower. It's a physical necessity.
This is the big mind shift right here. You have to flip your thinking. The low pressure isn't some weird side effect of the fluid moving fast. No. The low pressure zone is the cause of the high speed. It's like a little vacuum up ahead that's actively sucking the fluid forward, forcing it to accelerate into that tight space.
Okay, so that was the mechanical, force-based reason. But there's another, equally powerful way to look at this, and it involves zooming way, way down to the molecular level. It's all about trading one kind of energy for another.
Think of it this way. Pressure is really just zillions of tiny molecules bouncing around in all directions, slamming into the walls of the pipe. In that wide, slow section, they have tons of this random sideways energy. That's what we measure as high pressure. But when the pipe narrows, all those molecules get funneled and organized into moving forward. That random energy gets converted into directed, forward energy. They're all so busy racing ahead that they just don't have as much energy left to push outwards on the walls anymore.
And that's just a beautiful illustration of the conservation of energy. You've got a total energy budget. If you spend more of that budget on forward speed, which we call dynamic pressure, you have less left in the bank for pushing outward, which is what we call static pressure. It's a simple, elegant trade-off.
So let's boil all this down into a handy study guide. If you want to lock in the why behind the Venturi effect, you just need to remember these two core ideas.
So here it is. Number 1, the mechanical reason, coming straight from Newton. You need a force to accelerate the fluid, and that force comes from having lower pressure up ahead to pull it forward. And number 2, the molecular reason, all about energy. You trade random, sideways energy, static pressure, for organized, forward energy, velocity. Force and energy, two sides of the same incredible coin.
And that leaves us with a really cool final thought. Now that you know the lower pressure is the cause of the speed, not just a weird side effect, start looking for it everywhere. Think about an airplane wing. The air has to travel faster over the curved top surface. So, is the wing being pushed up from the bottom, or is it actually being pulled into the sky by that low pressure zone it creates on top? The answer is everywhere once you know how to look.